This is section 4.13, behavioral modeling. Behavioral modeling represents digital circuits at a functional and algorithmic level. It is used mostly to describe sequential circuits, but it can also be used to describe combinational circuits. Behavioral models execute one or more procedural statements when launched by a sensitivity mechanism, commonly called a sensitivity list, which monitors signals and launches execution of the behavioral description. Procedural statements are like those found in other programming languages. Procedural statements are like those found in other programming languages. For example, assignments and statements which control the sequence of execution. For example, for, loop, case, and if statements. This section considers behavioral modeling of combinational logic. Behavioral modeling of sequential logic will be considered in later chapters. Now, Verilog, behavioral descriptions are hardware declared with the keyword always, followed by an optional event control expression, sensitivity list, and a begin and end block of procedural assignment statements. Verilog has two types of assignment statements, continuous and procedural. We have seen that the continuous assignments use the keyword assign and the equals. Procedural are those made within the scope of an always or initial procedural statement. Procedural statements may use a blocking assignment operator equals or the non-blocking assignment operator less than equal, depending on whether the assignment represents sequential or concurrent behavior. And the event control expression procedural statement effectively specifies when the associated statements will begin to execute, because it suspends the execution of procedural statement till one or more of the signals of expression has an event, qualified or otherwise. In its absence, the associated statement begins execution immediately at the beginning of the simulation. This, I'm not going to go over it, but the VHDL is what this example is. It's the process where, or the Verilog is different. Okay. Now this, let's see. Process executes once at the beginning of simulation, therefore its sensitivity list determines when associated begin and end block statement will execute. Process executes when signals in its sensitivity list changes. For example, like a clock will start executing an event. This next HDL, examples 4.8, presents behavioral models of combinational logic. Behavioral modeling is presented in more detail in 5.6. After sequential circuits, alternative. Okay. Doesn't refer to it, but we talked about this before, the 2 to 4 line decoder. And so up here we declare a module, give it a name, got our output. This bracket here, 0, 3, you can think of it as an array, like D0, D1, D2, D3. And then we got our input, A and B is coming in, and the enable. And the enable is the kind of the trigger behind it. I don't know if that talks about it, but guess it doesn't. But anyway, with non-blocking less than equal assignments, the order in which assignments statements assigning values to the bits of D are listed does not affect the outcome. Again, you can think of this as like a clock that's telling it when to run. It runs every second, runs every 2 seconds type of deal. So we're controlling it with that. And so we got to always go in here. So, and then once it's enabled, then it actually runs this and does this calculation. What would that be? A prime plus B prime, and then a prime on that, and then enable on that. Now the prime is be at the very end, but enable is what triggers it then. So, and that's how it calculates those. Page is this? 217. Not that wrong section. What did this? So say it didn't look familiar. No, where in the world is that? Trying to find a Boolean expression for that, but I can't. Hopefully the site didn't just go down. There it goes. But anyway, if I were to look at the Boolean, this is what it gives us. So the Boolean expression would be these written out. And you notice they're all different. This is B prime, while this one's B. This is A, while these two are A prime. So it goes through our different choices. Okay, so this is that was a decoder. Maybe that's why I was having trouble finding it. 217. 2 to 4 line decoder. 2 to 4 line decoder. What in the world is this? Still doesn't give us the Boolean. Well, I can derive it. Let me grab a picture of this. I just wanted to show you they're not doing anything new. They're just using the old um, configurations that we've already talked about. 217. Okay. So for this one, I actually could say you got D here. So D0 to D3. So if I looked at just the D0, it's coming in from here, coming in from here, here, and here. This is A prime, this is B prime, and this is our enable. And that's actually E prime also. So that's why there's an exclamation in front of the A, in front of the B, in front of the enable. And then at the very beginning is an exclamation. And that's because there's a circle on the front here. So that's our inverter. So if I were to trace each one of these, all of these would correspond to the Boolean expressions with these. Okay. Now 2-to-1 line multiplexer. This shows you the use of an if statement. So we have our module up here, output, M out. And again, if I brought up either the Boolean expression or so forth, we'd see how this works out. A, B, and select. And then this, I believe, is, I'm trying to remember what the register is. I think it's just a temporary. Signal M out in must be a reg data type is assigned a value by a Verilog procedural assignment statement. Okay, so that's used temporarily in here. It's kind of like a variable in a programming language. Okay, so kind of a temporary one you almost think of. So, well, after you write it out, it's done then. Okay, so comes down here, and we got our always. So there's something that's going to trigger this to occur. And A or B or select, so bring that. And down here I'm checking if the select is equal to 1. Now again, what that would look like in terms of circuitry is it look like voltage is so high and it's equal to 1. Then your M out is going to be equal to A. Otherwise, it's going to be equal to B. So just a simple if statement based upon voltages coming into it. Notice this says if select is equal to 1, M out is equal to A. But then they talk about down here, if select M out is equal to A. This statement implies that select is checked for logic 1. And you see this in higher level programming languages, where if it's a Boolean, true or false, 1 or 0, you can check the Boolean. You could say if flag is equal true, then do this, or you can just say if flag, and then it runs it. Okay, I can cover the VHDL. 4 to 1 line multiplexer, 219. Okay. 4 to 1 line multi. I don't remember this, to be honest. 4 to 1 line multiplexer. Okay. So we have our output. That would be corresponding to this. And we got our input, N0, N1, N2, N3. And that should correspond to these inputs over here. In addition, we have a select. Oh, up here. Looking in the wrong place. Select. Trying to remember the format of the select there. Here I have two select criteria, but they're just doing it based upon passing in 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so then down here we got our always and got that, and that's a comment from Verilog to the syntax, and then case select. And to be honest, I don't know what this looks like in terms of circuitry. I don't know if you have like voltage coming in and for a certain time period, and then voltage following that, and that's how you interpret this or what. But anyway, this B00 you see right here corresponds with the 00 right here. And that tells us that we just send the I0 to our output. Now, if you got 0, 1 coming in to the select, 0, 1 is right here, and that says you're going to have I1 go to your output. And same with the rest of these. Does that make sense on what that's doing? Yeah. Okay. I really don't know why they didn't have two input selects. Maybe they can't. Okay, so case X, case Z statements. Case is pretty obvious, but the Verilog case construct has two important variations, case X and case Z. The first will treat as don't cares any bits of the case expression of case items that have logic value X or Z. The case Z construct treats as don't cares only the logic value Z for the purpose of detecting a match between the case expression and case item. List of case items need not be complete if a list of case items does not include all possible bit patterns of the case expression. No match can be detected. Unlisted case items, that is, bit patterns are not explicitly decoded, can be treated by using the default in the last item. Okay. Well, they don't have a Verilog example. Huh. That's EHDL. Oh, covered, I guess, in 5.6. That's why they just talk about it, but don't actually present it, I guess. Okay, test bench is an HDL program that describes and applies a stimulus to an HDL model of a circuit to test it and to observe its response during simulation. Test benches can be quite complex and lengthy and may take longer to develop than the design that is tested. The results of a test are only as good as a test bench that is used to test the circuit. So care must be taken to write stimuli that will test the circuit thoroughly, exercising all the operating features that are specified. And they present some examples here. In addition to employing the always statement, Verilog test benches use the initial statement to provide a stimulus to the circuit being tested. So this shows you an example from Verilog. So we've got to begin, A is equal to 0, B is equal to 0. And this refers to a time element. And they tell you up here, somewhere. And the rest are delayed by a given number of time units, as specified by the symbol £sign. Trying to think what that is over in the other package. It's some kind of seconds. Remember the simulation we would do? Let's see. Model sim. And error load and design. It has expired. That's great. I probably have to reinstall it. Oh well. But anyway, when we did the simulation, I remember when I installed this actually. When we did the simulation, it would specify how long we want to run the simulation. Well, you can uh, with your testing criteria, you can specify how long for it to wait. And that's what this is doing. And at that point, it changes just A. And then after 20, it changes A to 0 and B to 1. You might say, well, that doesn't seem very complex. Well, yeah, but we're testing just as like an OR gate or an AND gate or something like that. Yeah, there isn't a whole lot in your testing that you need to worry about. But if you have something real complex, that's what they're talking about. Let's see, for this one, the similar runs, a 3-bit vector D is initialized as 000. And repeat is a looping statement. D is incremented by 1 7 times. Once every 10. Okay, so this repeat here is based upon what's beneath it. So it'll do this. After 10 time units, it'll keep adding 1 onto there. And that shows a looping from 000 to 111. Because we know there can be a lot of possibilities on some of these. And there's the form. And this just talks about how you have your stimulus that gets affected, and it goes through and tests your code. That shows the general syntax of it. You can have displays in there, so you know what's running. And if you have a logged out, then you can see that too. Okay, PHDL we're not going to cover. Okay, so up here we got our design. And then down here, we got our T-select. Now this T-select down here, trying to remember the connection between these. T multi-X 2X1 DF. Okay, they have it down here. So 2X1 DF, and then our M out, A, B, and select. And see if I explain that. Note that a monitor system task displays the output cause book. Okay, figured that. Commented alternative statement having a display would create a header that could be used as a monitor. Okay. So it sounds like the monitor is what is actually calling it. This looks like there's too many parameters there. Oh, here it is down here. Look at the wrong line. So we got A, B, T underscore select. It almost feels like it's in reverse order though, than that, or not quite reverse, but the select and the out are reversed. I don't know on that. Doesn't really explain how the connection's made. We're not gonna be doing any of that, but okay. Logic simulation 4.15. Logic simulation provides a fast and accurate method of verifying the model of a combinational circuit is correct. Creates a visual representation of the behavior of a digital circuit by computing and displaying logic values corresponding to electrical waveforms in physical hardware. Two types of verification, functional and timing. In functional, we study the logical operation of the circuit independently of physical timing delays of gates using so-called zero delay models, which ignore the propagation delay of physical gates. Timing verification studies a circuit's operation by including the effects of delays through gates, and the process determines whether the specification for the operating speed of the circuit can be met. For example, must determine that the clock frequency of a sequential circuit is not compromised by the propagation delay of signals from a source register passing through the combinational logic before reaching the destination register. And timing verification beyond the scope of this text. Logic simulation is usually accomplished with event-driven simulators. At any instance time, most signals, gate outputs, and digital hardware are quiescent. I can't say that word. That is, they do not change values. Since relatively few gate changes at a time, logic simulators exploit this topological latency by using an event-driven scheme to which a computational effort is expended only by those times at which one or more signals change their values. Event-driven simulation is the main reason why it's feasible to simulate a logical behavior circuits containing millions of logic gates. Let's see. Simulation monitors signals A and B, and when they change, it determines whether to schedule a change for signal C. When the scheduled change in signal C occurs, the simulator schedules an event for signal D, and so on. So that's what they're talking about on that. Okay, this example here shows the output waveforms that are produced by a AND invert circuit having zero propagation delays when input waveforms are shown. The shaded area denotes the X value of a signal. The event time list and associated data structure show which signals have an event. It's convenient to display this relationship on a simulator time axis as depicted in the figure. At a given event time, the signal change list has been ordered to illustrate the causal relationships between the scheduled changes. For example, at time 20, the change of signal B causes a change in signal C. Here's the time down here. And so initially, at time 0, they're all set just to X. But then, after 10 time units have passed, then A and B are changed, which causes a change in C, and D. Now I notice A is 1, so the voltage is up here. B is 0, so the voltage is down here. And C is 0, so the voltage is there. And D is 1, so it's up here. And that makes sense when you think about it, because an AND gate, 1 and 0, 1 times 0 is 0. So C would be 0. But then you send that 0 through this inverter, and D becomes 1. Now here at time unit 20, B is changed to a 1. Now A hasn't changed, so A is still a 1. So we got 1 and 1 gives you 1. So that's why C becomes a 1, and D is the invert of C, so D is 0. And you see that these are up. A is still up here 1. B is now up here 1. C is 1, and D is 0. And then at time unit 30, it changes again. They set A to 30 or A to 0. So A goes down here. B is still at 1. 0 times 1 is 0, so that's why C is 0, it's down. And D is the invert of that, so that's why it's up. And then last, at time 40, B is equal to 0. So we drop B down to 0, A is 0. I haven't seen any kind of tool that gives you a visual representation of this. Logic simulator must manage the scheduling events for all the signals in a circuit that's being simulated. You can't just trust that things will arrive when they will. Part of your circuit design's got to be such that you control it. So let's look at another example. Event-driven simulation with propagation delay. Oh, the number here. Okay, so here, A is set to 1 and B is set to 0. And of course, 1 times 0 is 0. But C doesn't actually get changed until 3 time units, since our propagation is 3. This would be 13. And that's when C goes to 0. And I actually have it here. Here's 13, it goes to 0. Now it comes into here. And C is still 0. And at 15, D would become 1. So let's see. 15, follow the lines. D is 1. Must be 15 there, assuming. No, 15's over here. Never mind. And it goes to 1. So that just indicates the propagation delay. And how when this changes, this represents 3 time units here. I don't know why I don't have an arrow here. Let's see. Stimulus for the circuit is listed in the second module. The inputs are specified with a 3-bit reg vector D. D2 is equivalent to input A, D1 is a B, and D0 to C. Outputs of the circuit, F1, F2 declares type wire. And they got all your gates defined there. This is our stimulus. So passing in a binary 0, 0, 0 into D, or setting it equal to that to begin with. And then after 10 time units, D is equal to D plus 1. Okay, that's adding in binary 0, 0, 1, I guess. Okay, repeating that for the 10 time units, or after 10 time units. Okay, that has nothing to do with that up above. The 7. That's just cycling through all the possibilities. And 10 there. That 10 there would have nothing to do with that 10, 20, 30, 40 up above either, I don't believe. That just means if you run one, then run another, then run another, and so forth. Maybe that has nothing to do with this one. It just doesn't seem to coincide with that. That's probably just an example. HDL, and I can cover that. I think that's the end of the chapter. Yeah. Next chapter gets into synchronous sequential logic. There's parts of this we don't cover. I have to look that up. Wichita State told us what to cover on these and so forth. Handheld devices, cell phones, navigation, receivers, personal computers, digital cameras, personal media players, virtually all electronic consumer products have the ability to send, receive, store, retrieve, and process information represented in binary format. Technology enabling and supporting these devices is critically dependent on electronic components that can store information, that is, have memory. This chapter examines the operation and control of these devices and their use in circuits and enables you to better understand what's happening in those devices when you interact with them. Digital circuits considered thus far have been combinational. Their output depends only and immediately on their inputs. They have no memory. That is, they do not depend on past values of their inputs. Sequential circuits, however, act as storage elements and have memory. They can store, retain, and then retrieve information when needed at a later time. It's important you understand the distinction between sequential and combinational circuits. So this will be where you send an output to your circuit, and it circles back around, and it's your input to that same circuit. That's what they're referring to. This is what we're talking about here. You have your circuit here, and its output is going into memory, which then cycles back into your input to that circuit. These just kind of really throw me at first. I can understand it when I follow the logic, but it just seems strange the fact that the first time through, when you think about like you can turn on a device, there is nothing in memory, so there's nothing coming through. I can sit there and read all that to you. This is one method of controlling. You have clock pulses, so you have some kind of clock going through, and it's at certain intervals it's sending through voltage. That's what these high peaks here represent. And when those clock pulses send in those voltage, this is into what's called a flip-flop. Then the output from the combinational circuit then goes back and becomes your input. So it controls that. Now up here, the storage elements used in clock sequential circuits are called flip-flops. A flip-flop is a binary storage device capable of storing one bit of information. So we're not talking that this is a hard drive. So it's one bit information is storing. Let's see. Sequential circuit may, or the output of a flip-flop. In a stable state, the output of a flip-flop is either 0 or 1. A sequential circuit may use many flip-flops to store as many bits as necessary. For example, word of data may be stored as a 64-bit value. And that shows you that. So let me click on that. There it goes. And I don't know if I can get through this. SR takes some explanation. So I think I'll stop there. I'm going to put out the test for the chapter 4. Now the chapter 5 we'll have a test over. We'll finish this, and then the final exam is not going to be comprehensive. It's just going to be over the last chapter, chapter 6. And I'll probably put that out next week. So if you want to start working on it and start reading chapter 6 and get that out of the way, then you can. But we'll go ahead and stop there.